Hi everyone, welcome to Chapter 5, Continuous Random Variables. Continuous probability functions, what we're doing in this chapter. Properties. The graph of a continuous probability distribution is a curve. The probability is represented by the area under the curve. The curve is called the probability density function, the PDF, where you can use a function notation to represent the curve like f of x. The probabilities are found for intervals of x values. So, the probability c less than x less than d is the probability that the random variable x is between c and d. So it's the area under the curve above the x-axis to the right of c and left of d. So, to the left there, I did a shaded region, that green region, the area of that is going to represent the probability x is between c and d. If I ask you for the probability x equals an exact value with a continuous probability distribution, it's going to equal 0 because a line segment has no area. All right, and the probability that x is between c and d, including c and d, is going to be the same as the probability x is between c and d, not including c and d. All right, so I hope all that made sense. The first particular kind of continuous distribution we're going to do is the uniform distribution. So, the uniform distribution is a continuous probability distribution with events whose outcomes fall within an interval of numbers, each equally likely to occur. So this uniform distribution looks like it goes from 2 up to about 8 3/4 or so. So that the area of that rectangle there represents the probability x is between 3 and 6. So the notation we use, x equals u, standing for uniform, a to b. So a is the low number, b is the high number. So this example would be u 2, 8.75. All right, the PDF is always f of x equals 1 over b minus a, for a less than equal to x less than or equal to b. The mean is just the midpoint between a and b. So a plus b over 2 ends up being our mean. The standard deviation is radical b minus a squared over 12. You're going to have to compute both of those by hand. In fact, there is no fancy calculator function for this chapter. All right, we're basically going to be doing everything by hand. All righty? Here we go. Suppose you enter a building and want to take an elevator to a desired floor. Assume the elevator arrives uniformly between 0 and 40 seconds from the time you push the call button. So x is a uniform distribution running us from 0 to 40. So the mean is halfway between 0 and 40, or 20 seconds. The standard deviation, you do 40 minus 0 squared. Take that, divide it by 12, take that, square root it. All right, so 11.5 seconds ends up being the standard deviation. The probabilities, we are going to use this pretty simple formula to find probabilities. Probability that x is between c and d equals 1 over b minus a times the length d minus c. All right, so let's do an example. Suppose the time it takes for a student to finish a quiz is uniformly distributed between 6 and 15 minutes inclusive. So that x equals the time it takes a student to finish the quiz. So x is a uniform distribution running from 6 to 15. I drew it, so it's just a rectangle that goes from 6 to 15. The height of that rectangle is always going to be 1 over b minus a. So the height of that rectangle is 1/9. Because, and I didn't state this earlier, but the whole area always has to equal 1. Because that's what the probabilities all add up to, is 1. Okay? In any distribution function, the probabilities always add up to 1. So the area of that rectangle has to be 1. So if you take the length 9, multiply by the height 1/9, that equals 1. So now we can calculate various probabilities. What's the probability a student needs at least 8 minutes? So probability x is greater than or equal to 8 is the same as the probability that x is between 8 and 15, because 15 is the upper end of that uniform distribution. So applying the formula, 1 over b minus a, so that'd be 1 over 9, times d minus c, 15 minus 8, that's going to be 7. So the probability is going to be 7/9 that a student needs at least 8 minutes. Now we can do conditional probabilities in this one. What's the probability that a student needs at least 8 minutes given she has already taken more than 7 minutes? She has already taken more than 7 minutes. What this does, everyone, is it basically resets the rectangle. So since we know she takes more than 7 minutes, we could do the rectangle starting right there at 7 instead of 6, okay? And then we can do the problem the same exact way we did it with this new rectangle. So you see here, instead of 15 minus 6, we have 15 minus 7, because we already know she took more than 7 minutes. So the probability she takes more than 8 minutes, given she already took more than 7, be 1/8 times 7, so 7/8. All right, so it's tricky, but we should be able to get it if we really understand what conditional probability is trying to ask. All right, let's do another one. The amount of time in minutes that a person must wait for the bus is uniformly distributed between 0 and 15 minutes. So the first quartile, probability x is less than q1, has to be 0.25. So we could use the formula again to find this first quartile. Remember what that means is 25% of the data is less than whatever number we're coming up with. All right, so I need the probability of x being less than the first quartile to be equal to 0.25. Well, our rectangle goes from 0 to 15, so 1 over b minus a is 1 over 15 minus 0. And then the length between q1 and 15, q1 minus 0 here. And then I can solve that equation using my algebra skills. So 1/15 times q1 is 0.25. Multiply both sides by 15. So 3.75 minutes ends up being the first quartile. And if you use common sense, that should make sense as well, because 3.75 is a quarter of the way between 0 and 15. 90% of the time a person must wait is below what value? So they're asking us for the 90th percentile here, so I can run the same exact equation. So probability our value is less than P90. P90 is the 90th percentile. I do the same exact formula, and 13.5 minutes is what I come up with. Now let it be known, y'all, that a lot of times the uniform distribution doesn't start at 0. So be careful when you do these problems, because you could set it up the same way, except these zeros would be different, right? Like if it went from 1 to 15, you'd have 1 over 15 minus 1 times P90 minus 1. Then you'd have that one extra step, right? If I had P90 minus 1, right, let's see, if I had P90 minus 1 times 1/14, say, and it's supposed to equal 0.9, right? I'd multiply by 14 first. Let's see, what's 0.9 times 14? It's like 12.6, I think, or 0.126. 12.6, and I'd add 1. 12.6, not 1.26, so I get 13.6 would be the 90th percentile in that case. So just be cautious of what it's asking you to do, and this section should be pretty straightforward. Reach out if you have any questions. That's a pretty short lesson. We'll see you in chapter 6.